Hi guys, my name is Mharjay. I'm the Torre from BSCS3A. So I'm going to discuss about formal languages operations with words. So let's start. In automata theory, a formal language is a set of strings of symbols drawn from a finite alphabet. A formal language can be specified either by a set of rules, such as regular expression or a context-free grammar generates the language, or by a formal language that accepts or recognizes the language. So I have here the basic theoretical review of formal languages. The alphabet is the finite set of symbols. Word is the finite string formed from the alphabet. Language in any set of words over the alphabet. So under the formal languages, concatenation. Concatenation is um, combining two words or combining one object or one word to another. For example, I have here the snow and ball. So the output is snowball. So in formal language theory and computer programming, string concatenation is the operation of joining, from the word joining, join, character strings end to end. Joining the string end to end. For example, as I said earlier, the ball and the snowball in certain formalizations of concatenation theory are also called string theory. So concatenation theory is also called string theory. Character string theory or theoretical syntax studies character strings over finite alphabets of characters, signs, symbols, or marks. String theory is foundational for formal linguistics, computer science, logic, and mathematics, especially proof theory. So concatenation is used especially for proof theory, more on proof theory. So I have here the example of concatenation. Set A, we have the mango and orange. And for the set B, we have the green and orange. So if we concatenate the set A and set B, this is the result. Set A concatenate of set B, and mango green because we get the mango and the green. So we have the mango green. Next, the mango and orange. We have the mango orange, orange green, and the orange orange. So that's the concept or the idea of concatenation. Examples of concatenation in a sentence. The student's concatenation of the words air and airplane form the word airplane. Simple as that. Next, after her marriage, a concatenation of the woman's two last names formed a brand new one. So that's also a concatenation. Next is example of concatenation in a sentence. Concatenation of the Scrabble tiles join the word journey and the last word Y. We're going to we're going to concatenate it, the word yearning. Next is to save space, the Java programmers created a concatenation and strung several characters to string together. So next, I have here the concatenate example for Word Excel. So as you can see, we have here the set A and the set B. So you can see that those names, and this is the formula. So we combine the name David and his last name, we concatenate it, and so that the result is David White. Next is the powers of an alphabet. If sigma is an alphabet, we can express the set of all strings of a certain length from the alphabet by using the exponential notation. Sigma to the power of k, the set of strings of length k, each of those is in sigma. Examples, we have the sigma power of 0. Regardless of what alphabet is, that is the, what you call this? Epsilon is the only string of length 0. If sigma is equals to 0 and 1, then number 1, we have the sigma, power of 1, 0, 1. And then, as you can see, it has a pattern. Sigma, sigma squared. So that's 0, 0, 0, 1, 1, 0, and 1, 1, 1. And sigma cube, we have the 0, 0, 0, 1, 0, 0, 1, 0, 1, 0, 0, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. As you can see, it has a pattern. Note confusion between sigma and sigma 1. Sigma is an alphabet. Its members 0 and 1 are symbols. Sigma to the power of 1 is a set of strings. Its members are strings each of that. So next is the word reflection. Word reflection, bx is equals to a sub 1, a sub 2, a sub 3, and so on. A word, the reflected word of x is, so the reflected word of this or this formula is x to the power of negative 1 is equals to an, a3, a sub 3, a sub 2, and we just reflect it, or from the word reflection, we can see that we reflect the formula or the example. Word with the same symbol in inverse order. So this x to the negative 1 or to the power of negative 1 is equals to x. So that's the reflection of x. Next is the language L. A language over the alphabet, sigma is, or every subset of the universal language of the sigma. So this is the universal language. Every subset of words over a specific sigma generated from the alphabet of sigma. So union of languages. Union of languages, let L1, so this is, and L plus L2 be two languages defined using the same alphabet. So I think it's typographical error. So this is plus or end maybe. So L1, L sub 1, L sub 2, the universal language or the alphabet, the union of these two languages, L sub 1, L sub 2 is represented by L sub 1, or this symbol is the union of L sub 2 and defined by this, like this. So set of words from each one of languages equivalent to the plus operation. So here's the properties of union languages, the close operation, and the associative property. So this one, L sub 1 plus L sub 2 plus L sub 3 is equals to L sub 1 plus, so there. With neutral element, so this from the word neutral, so it's just nothing or 0 plus L, so that's L. And this, it's also a typographical, so it is commutative. Commutative, L sub 1 plus L sub 2 is equals to L sub 2 or L sub 1. So there, and idempotent, L plus L is equals to L. So simple as that. So there I have the operations with languages over a given alphabet. I already discussed the union of languages concatenation, power of language, or positive closure of a language, iteration or closure of a language, and the reflection of languages. So that's the end, and thank you for watching, and thank you for listening. Again, I'm Mharjay Del Torre from BSCS 3A. Thank you.